Hello. This is video 23, and I'm going to assume at this point you know video 22 by heart. What that was sort of showing us that we already knew more than we thought we did about binary addition. I said it loud, so I'll put an exclamation point. All we got to do is use circuits we've already done, and we black box them. We just say, I know how to do that. I can replicate that anytime I want. So let's pretend that we have black boxed those, and we're just going to copy those like cookie cutters every time we need them, one column at a time. I'm going to start way over here, since in binary addition we start on the far right column, so my inputs are going to look a little backwards. Let's say that my A bit, A that's in ones place on the place value chart, I'm going to call that A1. And I'm going to have to be very careful drawing this picture. I may not be very careful, but I'm going to try to be. Since the input's coming this way this time, I'm going to be moving from right to left. I'll put arrowheads on the inputs. You don't have to do that. But I'm going to do that to show that that's not an output at this point. That's an input into that box. Okay. And B1, the bit in the first column of the lower number. If this doesn't make any sense, this notation, then go back and do a quick rewatch of video 22, because I was calling the first 8-bit number capital A, the second 8-bit number capital B. This says get the ones place bit out of those. And this, 3 inputs, you might also recall I've got Cn. You know what, I'm just going to, no, I better call it Cn, because there's also a C out. Cn sub 1. I hope that's not confusing. That's quite a subscript there. That's A sub 1, B sub 1. That's C sub n, the input, the carry input, sub 1, meaning for ones place. Let's feed that into the calculating the carry out bit, COUT. Let's figure out what we need to carry to the next column. How are we going to do that? What's inside that box? Here's what's inside that box. That's the majority function, MAJ for short. First name basis, MAJ. Feed that into MAJ. Now then, that's not all we need. We need an answer. We need to know more than just to carry out. So I'm actually going to need 2 black boxes here. Not only that, and I hope I left enough space, I need to split off that A1, B1, C1 to feed those into this box as well. So I'll do that with nodes. We know what those are now. There, I broke off a piece. Here's A1's ones place bit going into this black box and also going into this black box. Same thing with B, same thing with C. In other words, we're using those same 3 inputs to feed that into 2 separate logical circuits. Why? Well, because we need 2 logical answers. One of them is to carry out to the next column. The other one is the sum bit that gets written down at the bottom. And the sum bit, I snuck that up on you. That's the circuit for example 2. Okay? So there's our 2 black boxes in action. What do we get out of it? Out of the sum bit, the output that squirts out of that is the sum bit that we write down at the bottom for ones place in our 8-bit binary addition. What else we need? Well, a bunch of stuff. Now that we've got all this calculated, well, wait a second, we don't have all of it calculated, do we? One of the things that we need for the next column over here, you'll recall, is the output, the C out. I'll make that a longer wire so I've got more room to work with. The C out becomes the C in for column 2's place. C in sub 2. Let me say that again. We feed that in to calculate C out for the first column. But whatever it is we're carrying out of ones place over to the 2's place column, that becomes the carry in to the 2's place circuitry over here. What's the 2's place circuitry? Well, this will C out for the first column. This will be carry out for the second column. I'll put 1 up there for that one. This is 2's place, 1's place down here. Just label as I go along. I'll also need to get the other 2 bits for column 2. So this arrow, I'll have to look and just see what that is. A for 2's place, B for 2's place, and voila, I've got the 3 inputs I need to start calculating the column 2 arithmetic. Got to do the same thing to get the sum bit down here. This is sum for 2's place. Example 2 is the alternative name of the circuit. The Cout was our majority function that you did for your lab assignment. And I'm going to have to move back the Cin, or I'm not going to have room for the node. I'm afraid of that. It's hard to squash all this on the board. It's just getting so complicated. That's a 2 there. It was a squashed 2. But the A2, B2, Cn2, those also need to be inputs to calculating the sum bit. That's a feeble arrow. There's a node off of B2 into the sum box, and a node off of Cn2 into the sum box down here. So what do I get when the smoke clears here? Spit out at the bottom. I get the sum bit, the 0 or the 1, that goes in 2's place. My 8-bit binary place value chart sum. This is looking pretty complicated, even though it's stuff that we've already done, and the idea is not that bad. Maybe I can explain it more clearly if I use more space when we go to the next column. It has to do all of this to figure out the stuff it needs to know for the first column. Carry a 1 or a 2 over to the next column, add that up with the 2 bits that were already in that column, and calculate a Cout bit to 4's place over here. I'll put this way over here. This will be the last one I'll do. So this will give me plenty of space to work with. This is the 4's place column. It'll be calculating Cout using the 3 inputs, still using our majority function. There's no reason to go back and rethink any of that. And it's got to calculate a sum bit to put at the bottom of 4's place. Like so. And since I've been labeling example 2 all the way across, example 2 is not a very enlightening name, but that's really what it was. If you go back and look, that's the logic we need for the sum bit. Now then, being very deliberate, what do I need to calculate? Let's forget about all that stuff. What do I need to be able to calculate what's going on in column 4's place? Well, I need the 2 bits that are in that column. It'll be the 3rd column over from the right. So I need the A bit. I made this longer on purpose so I could stretch it out. I need the A bit that's in 4's place value. I need the B bit that's in the place value chart 3rd column over. And I also need the carry in from the previous column. I think perhaps this is the most confusing part of the whole picture. Where do I get the carry into 4's place column to do the 4's place addition? I get it from the 2's place column. Whatever 2's place column is carrying out, that goes straight across. Shoot that straight across, and that becomes the carry in to this column, Cn sub 4. The carry out from column 2 is the carry in to column 4. Oh, and notice, just as a side thought here, there are no arrows at all going between these two. I think I said in the previous video, the calculation for the carry out and the calculation for the sum are completely independent of each other. They are completely independent logical calculations, logical circuits based on 3 inputs, but they don't know anything about each other. There are no arrows going back and forth between those 2 boxes. They have very different jobs from each other. But I do need to split off these bits here. I need some A4 going into the sum digital calculation. I need some B4 also going into the sum calculation, and some Cn sub 4 like so. What do I get after all of that work and all that connecting? I get a sum bit to write down at the bottom of my addition program, S sub 4, the 0 or 1 that goes in 4's place. And I get a carry out. I'll do the carry out. I'm not going to do all this other stuff. But I get a carry out that goes over to column 8. This will be Cn for 8's place in the place value chart. And it's dot time. Yada, yada, yada. This is enough machinery. Talking hardware here. This is enough machinery to do a 3-bit binary addition problem. Oh no, but we were going to do 8. Okay. Knock yourself out. Do 8 of these. 8 columns. 64 bits. Do 64 of these. It's called cascading. We're cascading our digital logic circuits because there's no reason to keep reinventing the wheel every time we move over one notch to the left. We just reuse copies of circuits that we already have. And tiny little microscopic AND gates and OR gates and NOT gates, those are not terribly expensive. We can replicate this for 128 bits and it's no big deal. It all starts over here. Zoom, it goes across one column. And now notice, it is going to have to go just like we are, just like humans do in binary addition. It's got to do this column first, otherwise it doesn't know what the carry in is to the second column. Then it does all this business, spits out a sum bit as part of the answer, and sends a carry in over to column 4, or column 4's place. It's actually only the third column. Got it? There. Well, addition wasn't all that painful, assuming all this made sense. We can now move on to other things. Conquered addition, conquered subtraction. We are moving along. I'll see you online.